let's look at chapter 3, patterns in scatter plots and correlation, and give you a quick recap of one of the situations. Suppose we had along the bottom age again. I like time, it's a good variable to have, and vertically, and we'll do height. And this happens to be the age and the height of some trees, and the data, at least the one I'm doing right now.
So this is recap?
Yeah.
Okay.
Right. So can you remember what name you gave to the horizontal axis, age? What kind of something variable is it?
Explanatory.
Explanatory. And this one is called the response variable, right? This particular data can be described by using a number of terms. We did these yesterday. Is this positive or negative association?
Positive.
Positive.
It's positive. I'm going to put bubbles around them for no particular reason. They look pretty. Is this linear or curvilinear?
Linear.
Is this fella strong, medium, or weak association?
Strong.
I would go strong. Moderate would be the next option, or moderately strong if you're one of those people who like to sit in the fence a little bit, right? Imagine that was there all the time. Does this scatter plot have an outlier? Kind of, yes, right? And it's this guy. Okay. So you are an outlier. And we pretty much, apart from giving you stories and saying, is this a positive or negative association? You know, like age against height of children would be positive association, right? You know, as you get older, right, you get taller, that type of thing. And that is kind of where we left off. So now I'm going to add some new stuff. If you take a set of data, you can find a line that goes through it. And let me tell you right now, I am talking only about linear scatter plots now. So let's forget about curvilinear for a minute. And what I'm dealing with here is only linear. If you have data and it's linear, you can draw a line through it. And this line has got lots of names to it. I wish I had only one, in which case I would tell you the only name you need to call it. But different textbooks have different names for it. So here are the names that we give to this line. Some of the names I like. I like this name. Would you agree that's a good name for that line? It's called the best fitting line. It's also called the least squares line. Don't like that name, but it's sometimes called it. It's sometimes called a regression line, which is a very common name. I don't like that name either. I like names to give me an idea of what I'm talking about, but you are going to hear or see in different textbooks and videos that you might watch, them describing this line, but they're going to say, oh, the least squares line is, and you're going to say, what's that? Oh, it's that guy. Or the regression line is, and you're going to say, oh yeah, it's that line, right? So it's just different names for the same guy. I know there's another name in there, and for the life of me, I can't remember what it's called. And if it comes to me, I'll tell you. And if it doesn't, if you ever see a video and they draw a line through the data, but they call it something, you know it's this guy, right? That's the fourth one that I can't remember right now. These are the ones we're going to be using. I like best fitting line, but I'm probably going to use the regression line because I think that's the one that this particular textbook uses. If you hold on a second, I'll see if I can find what they do call it.
It is regression.
Regression. Okay, so they're going to call it a regression line, right? Or just the word regression, but mostly regression line. Wouldn't it be nice if we could find out the equation of that line? Right? Oh, excuse me. Hold on a second. Sorry about that. Hello. Hello. Yes. Yeah, we're okay. Sorry. I apologize. I normally would switch off my phone, but that was a phone call that I was kind of needed to get. But my phone is off now, so you've got my undivided attention. And isn't everybody allowed to have the phone go off once per quarter? Right, so I've had my shot. It's a little bit easier for the rest of you, because if you hit mute, I won't know, right? So you may already have used up your shot and I never knew. So back to this problem. I'd like to know the equation of this line, okay? And you cannot do it by hand very easily. There are calculations, but they're extremely laborious. And so what we would typically do is we would let WebAssign, Salt, do it for us. So if you hang in there for a second, I'm going to find a question and I'm going to show you where to go looking for this equation, right? So this one will do. Okay. Now, here we are looking at some data. It's housing data. So if ever you become a real estate agent, for instance, this is the kind of thing that you would do if you were trying to sell someone's house, right? So you've got the job of selling a house. One of the first things a person would like to know is, how much will I be able to sell my house for? And there are a number of features of a house that make that, you know, the age of the house and the location of the house, and, you know, how well kept it is, you know, things like that. But one of the biggest predictors of the price of a house is the size of it, right? How many square feet it's got. So we are talking funny money here. Orange County, California. In this particular one, it's 2010. So I bet you everything here is probably doubled in price or more, right? But in 210, these are the prices. A 2,336 square foot house sold for 453,000. We would call these comps. So you would find the person's house, right? And you'd get the square footage. That's pretty easy to calculate. And then you would go and you would predict, based on this data at least, what it would look like. So I'm going to hit the salt button. And boom. So what you can see here, once it's finished doing its thing, can you see the square footage and the asking price? Now, I'm going to show you what the scatter plot looks like first. Square footage goes first, and asking price goes second. What's wrong with that? Oh, because I want a dot plot. No, I don't. I want a scatter plot. There we go. There we go. Actually, not as good as I thought it was going to be. But if you look at this data, would you agree that this guy way over here is an outlier? Can you trust me that this data is sort of a kind of a linear, right? We'll pretend it is. So if you click on regression, remember regression line, regression. If you click on that, and the explanatory variable was square foot, and the response variable was the price, you get the same picture. If I hit that little box there, can you see the straight line that's the best fitting straight line? And if I go hunting for it, you'll get a whole load of other numbers. The ones that you're really interested in are kind of here. Asking price, you see that one there? So the formula would be, well, that's a lot, asking price in dollars. So I'm just going to call it price. And it's equal to square footage times 0.2823. So that would be 0.2828. And that's square footage. So I'm going to call that area. Plus, I'm just going to call that 53.5. So there is the formula that would represent that straight line. So let me return now back, and we'll look at how that formula for the straight line works. Right. So here it is. You very often put a little funny thing that looks like that on top of it. So you read that out as predicted price. And that's kind of a qualification. You know that that's not guaranteed that's what your house is going to sell for, right? You know, if somebody comes and wants to buy it, but somebody else comes and buys it, can you have a little bidding war and it goes up, right? Or nobody's going to buy it at that price, so you have to reduce it, right? But that's a kind of typical middle of the road price. And this is our formula, and I got it straight out. Now, if you were going to look at that as a math formula, with X's and Y's, it would look like that. Now, on the guy that we had, area was the X, and the price that it was going to sell for is the Y. So does this formula translate into that one? Can you see the connection? Right? The area is the X. Now, wouldn't this formula make more sense to people who are not into math? So we tend to write our formulas like this, rather than write them algebraically with X's and Y's. Now, since I've got that price, I can now figure out what the going rate for a particular house is. So I'm going to figure out how much I could get if my house was 2,000 square feet. Well, according to the formula, the predicted price is 0.2828 times the area plus another 53.5. Question?
Should that be plus 53.5 or minus 53.5?
It was minus. Well caught. Yeah, I can see it here. It says minus. So let's see what this guy looks like. 0.2828 times 2 helps when the calculator's on. 0.2828 times 2,000. Take away 53.5. And to the nearest whole number, 512,000. So in 2010, I could have sold that house for about $500,000. Now, can you see you could have figured out what a 1,200 square foot house would sell for, or what a 4,000 square foot house would sell for? Knowing the equation of the best fitting line, doesn't that help you to make predictions about all sorts of houses? Even if there wasn't a 2,000 square foot house in my original data, you know, that original data of like 10 houses. Now, here's some truisms. If I make one of these models and I only use five houses, would you agree that I could get a straight line? Would you also agree that I shouldn't like bet money on it? Would you agree that 5 houses are not a good sample size? Right. Just 5 houses. Wouldn't it be much better if you had like 50 houses or 100 houses? So the more numbers that you use to create your scatter plot, the more accurate this formula is going to be at predicting square footage. Does that make sense? If you're only using 5 houses, you'll get a prediction, but if you're using 500 houses, that prediction is going to be closer to reality, right? So one of the mistakes that some people make is that they collect, you know, they basically only collect a few data points, and then they use that to come up with a straight line, and then they start using it in ways that it was never designed for, or in some way making it seem like the answer is accurate, right? Oh yeah, I did this regression line, and the regression line said that your house should sell for 512,000. So you should put that up as your selling price, right? But if you only used 5 numbers, and all of the houses that you used just happen to be pretty old, pretty decrepit, can you imagine that the true value of house could be a lot more than the predictor? And couldn't you end up selling it for less than you could have got? Right. So be careful. Lots of data, much better than not enough. And the next thing is also, I'm going to get it from this fella, is a variable called the correlation coefficient. And it's normally used as a little r. For instance, you might get a correlation coefficient of 0.3. So let me tell you about what information you get in this. If your data was a perfect straight line, right, every single one of them on the same line, the correlation coefficient is 1. If your data is linear, obviously, and nice and strong, you will get an R value somewhere between 0.9 and 1. So I want you to, if you can find this magic number R, and it's 0.92 or 0.97, that means your data is strong and linear, right? It looks like this. Now, if your data is moderate, but still linear, in other words, a fatter sausage, like this, then you are looking for 0.5 up to 0.9. And that would be moderate, right? And can I just draw a big balloon, right, like that? Wouldn't we call this weak? And weak is roughly in that region. And if you get a number that's less than 0.1, there is no association. So that would be a big circle of nothing. Right. So at least now, don't we have a kind of ruler to use, right? A number to use that we can then figure out whether it's strong, moderate, or weak. This one here, of course, is perfect, isn't it? It's a perfect fit, which you are not going to get in real life. Agreed? Have you ever done an experiment and every single data point was on the same exact straight line? Unless you were cheating, isn't everything always a little bit different, right? The best you can hope for is strong in real life, but that's what perfect looked like. Now, have you noticed that all those numbers are all positive? Because all my data is positive. I'm not going to go through the whole kit and caboodle again, but R is -1 if you have a perfect straight line going down the way. Can you imagine me drawing this data but going downhill? You would get -1 to -0.9, -0.5 to -0.9, -0.1 to -0.5, and basically won't the negative R values match the same numbers, right? In other words, an R value of whatever it is can tell you two things. Doesn't it tell you how good the fit is, strong, moderate, weak? And secondly, doesn't it tell you if it's positive or negative? Right? So imagine I had some data and I didn't draw it, didn't give you a scatter plot, didn't even show you the data. But I told you its correlation coefficient was 0.85. Is that data positive association means that it's going uphill, or negative association means that it's going downhill? What does that tell you? Going uphill.
Positive.
Positive. Based on my scale, would that be strong, moderate, or weak?
Moderate.
Now, these are very vague rules of thumb. You know, you could go to another textbook and they might say, no, 0.8 to 1 is strong. I doubt it, but they might, right? Or they might say moderate is 0.6 to 0.9, right? They might tweak the numbers a little bit. You just need to look at what they decide it is. So we're going to use these ones, and we can disagree with WebAssign later if it says it's moderate and you think it's weak. Now, the guy that we just did with the house prices, they have a fella in that list, and he was called correlation. And underneath it, the number they got was 0.9128. So that means that this was in fact positive. And according to what they said, right now, it's strong. Now, I wouldn't have judged that on the scatter plot. Would you agree that the scatter plot kind of looks big dot up here and then like 5 or 6 dots down there, right? And the straight line went something, if I remember, went something like that. But nonetheless, for the time being, we're going to stick to that. And then I'm going to show you what the problem is. Do you know how outliers cause lots of trouble? They make the mean weird. They make the standard deviation weird. Well, they also make correlation coefficient R weird. You see this outlier that we had here? He's the main reason that's so good. That's an outlier. If I remove this outlier, right, just take it away from the data, we should get a more realistic picture about the other numbers. Would you agree that the numbers that were down here were not really tight as a line, right? They were pretty mixed up all over the place. So I'm now going to go back and see if I can make that happen to kind of prove my point. Right, so if I shrink this back just a touch. There. Can you see the outlier up here on the top right-hand corner? You can't
Yes,
see it, am I
This
not
week.
the screen yet? Let me get the screen sorted out. There. Can you see it now? Right, top right-hand corner, do you see that outlier? Do you see this bubble of data, which was everybody else down here? Would you agree they do not look strong? They should be a lot closer. But numerically, that outlier is what screwed things up. So I should be able to go back and hit data set. And the outlier was this 5,500, 1.5 million house. Do you see it? And I should be able to just hit delete and make it go away. And am I sure? Yes, I am. Okay. Now I'm going to go back to that regression. And now I'll put in the line. There, do you, oh, why is that still there? I made you go away. I did. Good. Okay, let me see if I can.
Reset that.
I'm going to just play about with a second and see if I can make that number redone. Yay! Okay, I had to just go in and redo it. Now, God, that's so hard to say. Right. If you look at this data, and I'll put in the line, would you agree that that data is nowhere near a 0.9? Now, if I look at the correlation, I don't know if you can see it because it's so tiny. I'll make it maybe a little bit bigger. But the correlation coefficient is now 0.1749. And doesn't that qualify as very weak? That is weak, but probably in very weak. So here is another truism. If your correlation coefficient isn't strong, right, 0.9 or better, then be very careful about using the formula, right? Because anything it predicts is very likely to be miles away from the correct answer, right? So can you imagine that I was using this data and I used it to pick a 2,000 square foot house, which would be around about 500,000, right? Could it easily be 750,000? Do you see that dot that's almost on top of it? That's how bad my prediction could be, right? Now, if I wanted to improve this prediction, wouldn't I collect 200 houses from the area and get a lot more dots? And that would hopefully make the correlation coefficient bigger. In other words, a better fit to the data. Are we good? So let me return to notes and try and put some of what we did in the form of a note that you can then go back and look at. Right. So, oh, a new term. Linear regression. That is scatter plots that are lines. So we're only looking at lines now, not curvilinear data. And we call those situations linear regression. So if you have data with an outlier, so with an outlier, the correlation coefficient could be quite high. Without the outlier, couldn't the correlation coefficient change a lot? Is that a truism? Right. Now, remember we had a problem yesterday about who is an outlier and who is not. Okay. Now, right now, I think everybody here will say, yep, you're an outlier. With this new dot that I've just put in, I'll call it dot number 1. Is dot number 1 an outlier? And most of you still an outlier? How about dot number 2? So forget about those two guys. Is that an outlier? Some of you are no, maybe 1 or 2 of you might say yes. Would you agree that we're entering that grey area? So is there a way that I can check or compare it, right? What you do is you find the correlation coefficient with that number. You then take that number away, right? You take that data point away and you get it. So imagine a different story. We've got a before and we've got an after. The before uses the point that you think might be an outlier, and the after, that's what happens when you remove the point. And let's suppose if you didn't do anything to it, that the correlation coefficient was that, and then you removed the point and the correlation coefficient looked like that. That's situation 1. And here's situation 2. The correlation coefficient was that, and then you removed the point and the correlation coefficient became that. Right? Before and after. Before and after. Which one of these two situations is evidence that the guy you got rid of was an outlier? 2. Can you see if it makes a significant effect on the correlation coefficient's value, right? That is a good sign that you are looking at an outlier. The minute you take any data point away, won't you change the R value a little bit, right? Like you'll change the average a little bit, right? That's going to happen, but would you agree it's a little bit? So that means that in that case, it was not. So can you imagine we had this guy, it made a big difference, right? This guy made a big difference. This guy didn't make much of a difference. This guy's not an outlier. This one is, right? That's how you would do it. Now, if you were calculating back to the houses story, shouldn't you throw away all the outliers because they're distorting everything, right? They're distorting how good your predictor is, right? They are wasting, cluttering up the information, and outliers have a bad effect. And so it's okay to get rid of them. Do you know what you're not allowed to do? Is imagine you're doing a physics experiment and you want desperately the data to be linear, right? Your formula, your theory says that X against Y is linear. So your data looks like this. Would you agree that's curvilinear? You see a curve? Now, if you were an unscrupulous person and you removed those 4 guys by pretending or lying or just saying it as outliers, wouldn't your new data look very linear? Do you see why you can't just throw away data points because they don't fit what you want to be true, right? They are never outliers. Not in a million years would you consider those 4 guys outliers. Would you agree they're very close to the other data points? There's nothing really exceptional. It's just that you are wrong. Your theory is wrong, right? The data is not linear. It's got a curve to it. So guess what? Why don't you just change your theory to fit the data, not change the data to fit your theory, right? That's the trick, right? Just change your theory. Your theory was wrong. Now, I can imagine if you spent 20 years of your life arguing vehemently that it's linear and it must be linear because, you know, that's what it has to be for my theory to work. Can you see the temptation to kill off the 4 guys? Because it doesn't work. Because don't other universities perform the same experiments and collect the same data? And they're going to, the guys in Japan are going to say, well, we duplicated your experiment and we found it was curved. And then Wisconsin says, yeah, we did it and it was curved. How come you got linear? Can we see all your data?
So at very least, they're going to assume that you're incompetent, even if
at least, or worse than incompetent, that you're deliberately lying, because your reputation in science is important, right? Can you imagine if you get caught, you know, doing nasty things to the data, people are not going to, you know, you could lose your job, I guess.
I'm also assuming that with things that have a lot of data, I'm assuming there's at this point, there's a lot of tests people have to look for where some people can find that sort of manipulation.
Oh, it's easy to find them. Do you know the first thing you need to ask? Give me all your data, right? Including your outliers. And then you can just put it in a scatter plot and you'll see it in a minute. Now, if they pretend that they never even collected that data, and they say, oh, that's all the data I've got, then I guess you wouldn't know until you performed the experiment yourself. But it would come out. I do know, since we're on this, and I might as well show you. Here is some data collected about each one of these dots is, let's say, is a year, right? 1991, 1992, right? Looks something like that. And this is the average temperature on the Earth. And what you can see here is that the Earth is warming up, right? And in the window of time, let's say this is from 1990 to, I know, the year 2000, right? Would you agree that based on that window, the data is pretty linear and it's going up, right? And you could then make a prediction about what the temperature was going to be in 2020, and your temperature would be this one. And these might be, you know, it might not start at 0, right? It might start at 55. And this goes up to, you know, maybe 56. So in that time period from the start to the finish, it's gone up 1 degree, right? Based on only the data that's here, right? You could do that. If you open up your data and you look at the average temperature over thousands of years, you will see the data looks like that. For instance, that's an ice age. And so is that one. And this would be, I don't know if it has a name, so I'm going to call it the hot age, right? When the Earth was warmer. And this would be another one where the Earth is warmer.
Global warming?
So if you are looking at it in this way, isn't this global warming? But what were you really looking at is only that window there. And in that window there, isn't the data linear and going up? So you have to be really careful about people showing you data. I want to see the big picture data, not just the small snapshot data. Because if that is the case, then won't we go for another couple of 100 years and warm up, in which case we'll hit a hot age. But then in the next 2,000 years, won't we probably have a decrease in temperature and we'll end up with yet another ice age? You know how many ice ages that we've had just as human beings? We've probably lived through about 5 ice ages. Only 2 of them were major ones, right? Really, really cold ice ages, but we've had many ice ages in between those. And I'm giving an example. Do you know the Sahara Desert, which is a desert right now? Do you know the Sahara Desert used to be a forest? Global weather change, right? If the temperature goes down, won't we all try and get back to Africa to get the decent weather again? Because Scotland, for instance, was under, well, whatever it is, 200 feet of ice up to about 10,000 years ago. So nobody lived in Scotland 10,000 years ago, not even Neanderthal, except the ones that were on top of the ice hunting polar bears or whatever. So be careful with your data. Always ask, what else could you tell me that gives me a better impression of what's going on? Now, it could be that we are in the global warming world, and well, we are, then that's fine. You know, do something about it. But where am I going with this? Yeah, here we go. Let's show you now some more homework questions. And here we go. Suppose that a regression equation, right, the best fitting straight line, is given as y equals, well, y is equal to weight, gotcha, and x is height. And the formula then is, I'm writing this down, the predicted average weight is negative 250 plus 6 times the height. Wow. And what are they measuring here? Oh, these are men 18 to 27. Okay. 18 to 29. Right. Let's use that formula to make predictions about what the predicted average weight of a particular person might be. So if you are 70 inches tall, which is a pretty tall person, then your predicted weight is negative 250 plus 6 times your height, which is negative 250, add 420, and negative 250, add 420. I am looking at 170 pounds. I have no idea how accurate that is, but if you're about 5 foot 10 inches, according to them, the average weight of an adult male is 170 pounds. I don't need to know your weight, it's all personal detail, but does that seem about right? Do you know somebody who's about 5 foot 10 and they weigh around about that? Or does that look like an under or an over? Is that pretty decent? Right, pretty decent. So you know what's going on there. Now, if you choose someone who's much taller, right, you would get an even heavier person, right? Because it makes sense, right? Taller people have more bone and more muscle, right? So that adds up to weight, right? Short people, not. Okay. So you can use it, and it looks like it's a pretty good predictor. And then they get one person, right? And this particular person is 7 inches tall in my story. So here's the first thing. That doesn't mean every single person in the universe who's 70 inches tall will weigh 170 pounds, agreed? Can you find somebody who weighs less than that and someone who weighs more than that, right? So in this story, we found somebody who was 70 inches and they weighed £173. There is a difference between those two. One word for that difference is error, right? Would you say that I'm £3 out? Right, I predicted 170, but for this one person, it's £3 out, right? For the next person I pick, it might be, you know, £10 out or £10 less, right? Something like that. The error has a different name. We call it the residual, right? So if they ask you to find the residual, they're just asking you to find the error. And you get it by taking away the real value minus the predicted value. Now, the real value in this case was 173, and we predicted 170. So the residual here would be £3. In other words, what we predicted £3 more than it was. Right. Now, if you've got a good model, wouldn't you hope that these errors are pretty small most of the time? Wouldn't that be a good model? And a bad model would be, well, you might predict that, but the real weight could be tons more or tons less. That would be a bad model. What would that look like? Well, if it was a good model, wouldn't you be getting data that was quite strong and linear? And if it was a bad model, wouldn't you be getting it because the data that you were using, because that's what life is like, right, is much weaker? So weak scatter plot, weak predictor. Strong scatter plot, strong predictor. Strong predictor means the predicted value and the true value are going to be very close to each other most of the time. A weak predictor would be the predicted value and the real value could be miles away. In lots of cases, they are miles away. Is that good? That makes sense? And I think that's perfect timing.